In mathematics, the binomial series is the Maclaurin series for the function given by, whereas an arbitrary complex number, explicitly, and the binomial series is the power series on the right-hand side of, expressed in terms of the binomial coefficients. Special cases: if alpha is a non-negative integer n, then the th term in all later terms in the series is 0. Since each contains a factor, thus in this case the series is finite and gives the algebraic binomial formula. The following variant holds for arbitrary complex beta, but is especially useful for handling negative integer exponents in. To prove it, substitute x equals minus z in and apply a binomial coefficient identity, which is convergence. Conditions for convergence: whether converges depends on the values of the complex numbers alpha and x. More precisely, if x less than 1, the series converges absolutely for any complex number alpha. If x equals minus 1, the series converges absolutely if and only if either e greater than 0 or alpha equals 0. If x equals 1 and x minus 1, the series converges if and only if e greater than minus 1. If x greater than 1, the series diverges, unless alpha is a non-negative integer. Assume now that is not a non-negative integer and that we make the following additional observations, which follow from the ones above. If e greater than 0, the series converges absolutely. If minus 1 less than re 0, the series converges conditionally if x minus 1 and diverges if x equals minus 1. If re minus 1, the series diverges. Identities to be used in the proof: the following hold for any complex number alpha, unless alpha is a non-negative integer. A useful asymptotic relationship for the binomial coefficients is, in Landau notation. This is essentially equivalent to the Gauss limit for the gamma function, and implies immediately the coarser bounds for some positive constants m and m independent of k, which are in fact sufficient for our needs. The simpler bounds may also be obtained by means of elementary inequalities. Proof to proven: apply the ratio test and use formula above to show that whenever alpha is not a non-negative integer, the radius of convergence is exactly 1. Part follows from formula, by comparison with the p-series with p equals 1 plus re. To prove, first use formula to obtain and then use an formula again to prove convergence of the right-hand side when re greater than minus 1 is assumed. On the other hand, the series does not converge if x equals 1 and re minus 1, because in that case, for all k, completing the proof of, also, the identity above, for x equals minus 1 and with alpha plus 1 in place of alpha writes whence follows using again. Summation of the binomial series. The usual argument to compute the sum of the binomial series goes as follows. Differentiating term-wise the binomial series within the convergence disk, x less than 1, and using formula, one has that the sum of the series is an analytic function solving the ordinary differential equation u equals alpha u with initial data u equals 1. The unique solution of this problem is the function u equals alpha, which is therefore the sum of the binomial series, at least for x less than 1. The equality extends to x equals 1 whenever the series converges, as a consequence of Abel's theorem and by continuity of alpha. History. The first results concerning binomial series for other than positive integer exponents were given by Sir Isaac Newton in the study of areas enclosed under certain curves. John Wallis built upon this work by considering expressions of the form y equals m where m is a fraction. He found that the successive coefficients ck of k are to be found by multiplying the preceding coefficient by, thereby implicitly giving a formula for these coefficients. He explicitly writes the following instances. The binomial series is therefore sometimes referred to as Newton's binomial theorem. Newton gives no proof and is not explicit about the nature of the series. Most likely he verified instances treating the series as formal power series. Later, Niels Henrik Abel discussed the subject in a memoir, treating notably questions of convergence, elementary bounds on the coefficients. In order to keep the whole discussion within elementary methods, one may derive the asymptotics proving the inequality with a m independent of k as follows. By the inequality of arithmetic and geometric means using the expansion the latter arithmetic mean rights to estimate its kth power, we then use the inequality that holds true for any real number r as soon as 1 plus r k0. Moreover, we have elementary bounds for the sums